All right, folks. So the energy unit, kind of the focus of that unit was the idea of conservation of energy and also the idea of work being a change in energy. Similarly, in the momentum unit, we're going to work our way up to a conservation law. So we have this idea of impulse being a change in momentum, but it also turns out that momentum is a conserved quantity. And so there are some things that make momentum easier to work with and some things that make it more difficult to work with. But what we're going to do in this lesson is to just establish the idea of conservation of momentum. And so we're going to follow the scenario of a car accident, essentially, um, and use it to demonstrate what conservation of momentum would look like in an equation form. And then we'll, like, in the next lesson, we'll talk about kind of the official definition and ideas and work with some examples. So our scenario, a truck of mass capital M and initial velocity vt naught collides with a car of mass lowercase m and initial velocity vc naught. Okay, so velocity of the truck, velocity of the car, there we go. Now, we'll imagine maybe that the truck is moving this way and the car is moving this way. So as far as the forces that act on the truck and the car, so the truck has a weight of big M times G and a normal force. The car has a weight of little m G and a normal force. Now those normal forces are different because the weights of the car are different. And then, they collide. So they are coming at one another. Maybe not, but we're going to imagine that they're coming at one another. And when they collide, right, the truck hits the car. The truck is to the left of the car. And so the truck gets pushed with a force, and that force comes from the car. So FC is the force of the car on the truck. And then the car, because the car is on the right side in our imagination, the car gets hit with a force that is the force due to the truck. And so those are the free body diagrams, not drawn to scale officially, of the two objects. And so we go all the way back to Newton's laws and establish what we know and work from there. So Newton's third law is about action and reaction force pairs. So once the truck and the car start to collide, they establish an action-reaction force pair. The force that the car delivers to the truck and the force that the truck delivers to the car have to be equal. So we know that the force delivered by the car is equal and opposite to the force delivered by the truck. So they are a force pair, and so they have to be equal. Now we looked at the graph, like an example graph of a force over time for a collision between two random objects, and it gave that like bell curve shape. It will still give that bell curve shape. Like the force will increase as the vehicles compress, and then it will decrease as they uncompress. But at all moments in time, those forces have to equal one another. Okay, so then we go to Newton's second law. And so as far as Newton's second law is concerned, we want to choose a system that we can analyze. Now this is two objects, and so going back to the forces unit, we got to choose. Do we analyze the truck, analyze the car, or analyze the system that includes both? So since we've spent the energy unit thinking about systems a little bit, we are going to analyze the truck car system. I failed to write the word car. The truck car system. And what we will find is the vertical net force on the system is 0, because this normal force is equal to the weight. This normal force is equal to this weight. So those add up to 0. And then because these forces are equal and opposite, they also add up to 0. So we have a net force of 0 on the system. And so following a Newton's second law analysis, if we added the force caused by the truck and the force caused by the car, because they are equal and opposite, they will add up to 0. And so this is where we build upon to get into the realm of impulse and momentum. So I'm going to take this entire equation and imagine, right, it was a collision, and so it must have happened over the course of some time. So we're going to multiply this whole equation by the amount of time that the collision would have happened. And so when we do that, we get the force delivered by the truck times time plus the force delivered by the car times some time equals 0, because anything times 0 is just 0. So we've now established, instead of individual forces, we have a word for this, and this is the impulse. So this is the impulse delivered by the truck, and then this is the impulse delivered by the car. These are equal and opposite impulses. So this is a key idea in and of itself, that when two objects collide, they have to deliver equal and opposite impulses. This is more or less an extension of Newton's third law. If the forces have to be equal, the forces also have to exist for exactly the same amount of time, and so therefore there have to be equal and opposite impulses on the two objects. And so this is an always situation, right? Because Newton's third law cannot be violated, there have to be equal and opposite forces on each object. There have to be equal and opposite impulses on each object. So, the thing about this is the force delivered by the truck, but it actually means that this is the impulse on the car, right? So this is the force that the truck exerts on the car. This is a force that the car feels, and so this term represents the impulse on the car. So using one of our new ideas from this unit, we know that impulse is equal to a change in momentum. So the force that is exerted by the truck is exerted on the car. And so the car experiences a change in momentum. If I go over to this one, this is the force delivered by the car to the truck. The truck also experiences a change in momentum, and those things have to equal 0. So I just kind of transposed. This is the impulse on the car. This is the change in momentum of the car. So another extension of the third law is they have to experience equal and opposite changes in momentum. So the idea is whenever two objects have an interaction that kind of falls under the general category of collisions. There's a few different types of interactions we're going to think about. But when there's an interaction between objects that results in a Newton's third law force pair, they deliver and experience equal and opposite impulses, and they deliver and experience equal and opposite changes in momentum. And so this kind of gets us to the door of momentum conservation. So I'm going to just expand this a little bit. This is the change in momentum of the car. So I can expand that. And so I'm going to go down here and go mass times final velocity minus mass times initial velocity plus, and then I'm going to put this next one here, big mass times final velocity of the, oops, let's try that again. Big mass times velocity of the truck minus big mass times initial velocity of the truck. So again, like change in momentum is mass times change in velocity, so mass times final velocity minus mass times initial velocity, and I do that for both objects. And again, this also has to add up to 0. To work with this equation, I'm going to play a little bit of a trick here and just kind of talk you through the algebra that I'm doing and the way I'm manipulating the equation. Is, these terms on this side of the equation are negative, so I'm going to take these terms, bring them over here by adding them to both sides, and then I'm going to just flip the equation around. So you're going to see like 2 steps of algebra, kind of 4 steps of algebra in one, but it's going to end up looking like this. It's going to say MVC naught plus big M Vt naught equals mvc plus big M Vt. This expression is kind of a generic expression for conservation of momentum, and it holds something very important because this set of terms, this is the initial momentum of the car, this is the initial momentum of the truck, this therefore represents the total initial momentum of the system. On the other side, this is the final momentum of the car, and this is the final momentum of the truck. This therefore represents the total final momentum. So we see an equation that presents similar ideas to conservation of energy. With conservation of energy, we had the initial mechanical energy, which was the total initial energy, equaling the final mechanical energy, which was the total final energy. And so now we have this idea of if our system includes two objects, if I add up their initial momenta before something happens and add up their final momenta before something happens, they will be equal. And so this is the idea of conservation of momentum. I think it's very important that you remember all of these things because they all go together and they're all really big physics concepts, equal and opposite forces. If they are treated as a system, their net force is 0. They experience equal and opposite impulses. They experience equal and opposite changes in momentum. And because of all those things, the total momentum stays the same. And so in the next video, we're going to work with kind of the official definition of conservation of momentum and some examples.